Okay, so I want to talk about Gauss's law and non-uniform spherical charge just distributions parts 2. Okay, so let's see how you would use what we learned in the last video for Gauss's law to find electric fields in there. So here's a sphere, and the charge is not uniform. The charge is as you go out, it gets greater and greater and greater. Now I'm not going to shade this in because we need this picture to be fairly easy to decipher. And so it's a radius r, and you should just keep in mind that as you go out, the charge density gets greater and greater until you get to 0. Okay? Now if I wanted to know the electric field, say right here, somewhere inside here, at a distance r away, lowercase r, this is what you do. You draw a Gaussian surface that's spherical, and you find all the charge enclosed in there. Okay, now you have to use the shell method to find that charge. Now I'm going to call this R. I'm going to call it RG for R Gauss. That's the radius of the Gaussian surface, because I have to put one more set of spheres in here that are going to represent a shell. So I don't know if you can see what I'm doing here, but this is a shell right here. Can you see that? That's a shell, a spherical shell. Whoa. And that spherical shell has charge embedded in it. And it's imaginary, but that's what what I'm going to do. I'm going to find all the charge in that spherical shell, and I'm going to add them up with an integral, but I'm going to tell the integral not to go all the way to capital R. I only want to know the charge that's enclosed here. So I'm going to tell the integral to go from 0 to R sub g. Okay, so this is the tough part here. The tough part is getting the charge enclosed. So the charge enclosed over epsilon naught is equal to E dot dA, Gauss's law, the closed integral of E dot dA. Okay, well, the charge enclosed is going to be, what I'm going to do is I'm going to sum that up using, it's going to be rho dV. So it's going to be rho, that's rho, times dV. Now dV is the volume of that shell. So the volume of the shell is going to be 4 pi r squared dr. So that's, and I put that all over epsilon naught. Okay, so this whole mess right here, that's getting me the charge enclosed by the Gaussian sphere. This r goes all the way to here. That's r. And same with that r. This tells me the density there. And I'm going to tell the integral to start at 0 and go to r sub g. This side is going to go, okay, let me give you the arguments for why the flux here. See, this is dA of the Gaussian surface. And it turns out that the E right there is also radially out. And that's because of a cancellation effect. The charge on the outside for a sphere, the charge on the outside, they all cancel out. So if I put a positive test charge there, all this charge would cancel with the other outside charge. And the only charge that would be pushing on it then is this stuff, the charge on the inside, which means that it would be pushed radially out. So E is in the same direction as dA at every point, and E is uniform at every point on here. So that is going to be equal to E times, if I pull the E out of the integral, if I add up all the dA's, it's just going to be 4 pi times r squared. That's the surface area of a sphere. It's just going to be the surface area of that sphere, rg squared. Okay, so that's the physics. Let's do the math. The math, I still have to do this integral. Okay, so I'll pull out all the constants out in front of this thing. So it's going to be b. I'll pull a 4, a pi, and a b out. And I'm left with the integral from 0 to r sub g of r cubed dr. And we got to put that all over epsilon naught, and that's equal to e times 4 pi r sub g squared. Okay, solving for this integral, I got 4 pi b, and when I solve for that, I get 1/4 r to the 4th from 0 to r sub g. You see how that's getting me the charge that's enclosed by the whole Gaussian surface? All right, and so all over epsilon naught, and that's equal to e times 4 pi r squared, r sub g squared. Okay, moving right along to the next part. All right, so let's substitute in for this. I guess we can get rid of the 4's, and we can get rid of the pi's. And so what I have here is b. If I put in the r sub g, that's going to turn into r sub g to the 4th. If I put in 0, when I subtract the 0, that term will disappear. So it's just b times r sub g to the 4th power all over 4 epsilon naught r sub g squared. Let's get rid of one of those r sub g. So the electric field is going to be b r sub g squared all over 4 epsilon naught. And there you have it. So as you go out, what happens to the field? As you go out, at least to r, apparently it looks like this. This is a constant, that's a constant, and that's a constant. So it's proportional to r squared. So it's going to look something like this. Okay. What about if you're outside of the sphere? Out here, what would the electric field look like there? Well, it's straight out, but the value of it, to get the value of it, I'm going to dot this and find the total flux through there both ways. So that's how you do a Gauss's law problem. You find the electric field both ways, and so let's do that. Or the electric flux both ways. And so that's going to be Q enclosed over epsilon naught is equal to E dot dA. Well, the dot product, E and dA are going to be in the same direction on here. The dA will be this way. And so will E. And E will be the same at all points on this Gaussian surface. So this is going to turn right into E times 4 pi r squared, where r is the radius of the Gaussian surface. Okay, to get the other side, I'm going to do the charge enclosed over epsilon naught. So the charge enclosed is going to be the sum of all the charges, beta r, that's the charge density, times the volume of each sphere, 4 pi r squared dr. That's the little volume. It needs a thickness, right? And I'm summing them up. So this gives me the charge in every sphere. And I'm going to tell it to start at 0, but you must stop at capital R. Don't go all the way to R. You'll be over counting. The integral needs to know that when it gets to capital R, it should stop adding them up. And so that's how you do that. This is the answer. This answer was in the last video. All right. Thank you for your time. Bye.